to speak back to back to each other. So without any further delay, I will give the floor to Mr. Gustavo Molina, please. Gustavo, please.
Good morning, everyone. I would like to start saying that thank you for the invitation. I am speaking for Dr. Javier Palacios, my institute director, which was unable to be here. I hope that we will be understanding very well each other, I mean, you and me, and I am open to questions. I understand that the questions will be at the end of the presentation. And well, let's start with the presentation, if you don't mind. Jan, can you share my presentation?
Gustavo, you just need to turn sharing on, share screen.
Yes, I see, yeah, okay. Okay, so let's start. The title of this presentation is Understanding the Nuclear Fuel Cycle. Let's see. First, we're going to talk about the timeline of nuclear power. Then the concepts as nuclear fission, nuclear energy, mining, milling, conversion, enrichment, fuel fabrication, irradiation in nuclear reactor, spent fuel storage, reprocessing, and disposal. Well, in the first place, we are going to, well, our timeline will include another things, but let's start with the first uranium atoms split for the first time. This occurred in 1939 in Germany. And it was the beginning of World War II, which detonated all these activities in the nuclear field. Then in the part of the US, they started the Manhattan Project, which was starting also in 1939 and finished in 1945 with the detonation of the first atomic bombs. In 1942, it was the first self-sustained fission chain reaction in the Chicago University. The first bomb used as weapon was detonated in 1945 in the Hiroshima and Nagasaki cities in Japan. In 1951, the experimental billet reactor was set up, and it was an experimental reactor. It was set in Idaho. In 1953, there were the first boiling reactor experiments. They developed first steam producing reactors. In 1954, it was published the Atomic Energy Act in the US. In 1955, it was launched the first nuclear power submarine. Then the nuclear industry, this is a gap here, developed and produced a lot of nuclear power reactors for commercial use, which now we are going to talk about three accidents that happened. One in 1979 with the 3 Mile Island, which produced a damaged reactor. In 1986, in April, the Chernobyl reactor suffered a vapor explosion, which destroyed the reactor and provoked a massive dispersion of fission products. In 2011, the Fukushima Daiichi reactors suffered a tsunami, which caused the damage of 3 reactors and the storage pool of another one. So this is more or less a quick timeline of nuclear power. We are going to talk about the nuclear fission. The nuclear energy is possible thanks to the reaction of nuclear fission. Nuclear fission is produced by neutron, normally slow neutron, low energy neutron, which introduces in atoms susceptible to be fissioned and partitioned. So the first nuclear fission was done in 1938 by Otto Hahn, that discovered that uranium-235 nucleus can capture a neutron that collides with it. It produces a compound uranium-236 nucleus, which is highly unstable. This uranium-236 nucleus quickly splits into 2 lighter nuclei, and at the same time, it releases 2 or 3 neutrons. This process of splitting of heavy atomic nucleus, such as that of uranium or plutonium, into 2 fragments of roughly equal mass is called nuclear fission. The process is followed by the release of a large amount of energy, approximately 200 MeV. We can see at the bottom this figure that represents the atom of uranium-235, which is being collided with a neutron. The neutron enters the uranium-235 and produces uranium-236. This is unstable, and this splits into fission fragments and several neutrons. You can see at the right of the slide the representation of this nucleus. In the left side of the figure, you can see several atoms, lighter atoms, and the other side also other atoms. These atoms are called the fission products. Well, the other reaction that can happen to the fuel, because the fuel is comprised of uranium-236 and uranium-238. The fissionable uranium is the 235. The other uranium, the 238, is not fissionable, but it can be absorbing neutrons, and it transforms to uranium-239, which is also unstable. It decays to neptunium-239, which also decays to plutonium-239. Why is important the plutonium-239? Well, the reason is that plutonium-239 is also fissionable. It means that as uranium-235, the plutonium can be used as fission atom. I mean, it can be done, it can be sustain nuclear chain reaction. And it's important for several reasons. The first reason is that it can sustain chain reaction and produces energy. And this energy can be used in nuclear bombs or, well, basically, as uranium-235 can be used in nuclear bombs. Both nuclides, both isotopes can be used in not only in nuclear reactors, it also can be used in nuclear bombs. So it is important of both isotopes. Well, the nuclear energy uses the energy of the fission to make nuclear reactors and to produce electricity from this nuclear energy. The nuclear energy is the energy in the nucleus or core of an atom. There is a huge amount of energy in an atom's dense nucleus. The uranium is the most widely used to produce nuclear energy. That is because uranium atoms split apart relatively easily. Uranium is also a very common element found in rocks all over the world. However, the specific type of uranium used to produce nuclear energy is called uranium-235. It is rare. Uranium-235 makes up less than 1% of the uranium in the world. Nuclear energy can be used to create electricity, but it must first be released from the atom in the process of nuclear fission. In a nuclear reactor, atoms of uranium are forced to break apart by neutrons. As they split, the atoms release more neutrons and fission products. Neutrons cause other uranium atoms to split in a process called chain reaction. The energy released from this chain reaction creates heat that is used to produce electricity. Uranium, in the right side of the slide, you can see, well, some properties of uranium. You can see the mass. You can see that this number, zeta number, is 92. It's the number of protons in the nucleus. You can see also that single pellet of uranium, which is part of the fuel in the nuclear reactor, is equivalent to about 150 gallons of oil, about 2,000 pounds of coal, and 17,000 cubic feet of natural gas. So the energy that is inside of the uranium-235 is huge. Is perhaps by weight is the order of 10 to the 6th times the energy stored in the matter. If we talk about chemical energy, so nuclear energy is several times, several orders of magnitude that energy that we can get from chemical reactions. Okay, the nuclear reactor is a class of devices that can initiate and control a self-sustaining series of nuclear fissions. Nuclear reactors are used as research tools, as a way to produce isotopes. and most prominently as energy sources for nuclear power plants. And the nuclear reactors use, as we see in the other slide, pellets as fuel. Today, 10% of the world's electricity is generated by nuclear power plants. But nations as France, Ukraine, and Slovakia produce most of their electricity from nuclear energy. This year, there are 441 power reactors in operation, and also 54 nuclear power reactors under construction. From 2016, there are 25 new reactors in operation in China, Korea, USA, India, Pakistan, and Russia. Thanks to the nuclear reactors, the releases of CO2 will not increase in 8% each year. Well, let's talk about nuclear fuel cycle. The fuel cycle starts with the extraction of uranium ore from the soil in a process called mining. In the milling, we concentrate this uranium ore in yellow cake, which is U3O8 molecule. In the conversion process, we convert this yellow cake in UF6. UF6 has the properties of being stable from the chemical viewpoint, and also it converts in gas at low temperature. Well, the next process in the fuel cycle is enrichment. We use this UF6 to concentrate uranium-235, which in nature is 0.7%, and it is enriched to 3 to 5% for use in nuclear reactors. The process more used is the cascade gas centrifugation, which demands big quantities of energy. Well, once the uranium is enriched, it is used to fabricate fuel. It changes to UO2 pellets because in the disoxide form, and it is a ceramic form, it is more stable at high temperatures, and it is the way it is used in most of the reactors. Then the fuel is put inside a nuclear reactor, which is used to produce energy. It reaches the criticality and produces heat. This heat is used to produce electricity. After the fuel is spent, I mean, it is not able to produce more energy. This fuel is stored to cool down in terms of radiation and in terms of heat production, and then it is reprocessed. This fuel is reprocessed by chopping. I mean, it's cut in small pieces, then it's dissolved in acid, and through several processes, the uranium and plutonium are recovered, and the fission products are immobilized, waiting for disposal. Well, the last step, last process, the nuclear fuel cycle is disposal as high-level waste. The disposal of fission products which are immobilized in glass, or as spent fuel it is declared waste. Several countries have decided to declare the spent fuel as waste. So either the fission products immobilized in glass or spent nuclear fuel are disposed in appropriate geological repositories. The main isotope to be controlled or isolated from environment is plutonium-239, which has a half-life of 24,000 years. Well, I'm sorry for the formatting. The mining of uranium is, the way it's taken from the soil. Uranium is very frequent in rocks. It's very abundant. Uranium is about 500 times more abundant than gold and as common as tin. There are 3 ways to mine uranium: in open mines, in underground mines, and leaching from the soil. I mean, the 3 options are represented in the figures to the right. The decision of which mining method is governed by the nature of the ore body, safety, and economic considerations. The largest producers are Kazakhstan, Canada, and Australia. The concentration of uranium of the ore could range from 0.03% up to 20%. Milling is done close to the uranium mine. And most of the mining facilities include a mill. The mined uranium ore is crushed and chemically treated to separate uranium from the waste rock. The resulting is a yellow cake. It's a powder, very yellow. The yellow cake is raised to more than 80%, and the original ore in comparison may be as little as 0.1% uranium. After milling, the yellow cake concentrate is shipped to the conversion facility. The remaining ore that contains more of the radioactivity and nearly all the rock material becomes tailings, which are placed in engineering facilities near the mine, often as a mined out pit. Well, the conversion converts the yellow cake into UF6. The UF6 are put in large cylinders, which at normal temperature are solid. And this is how they treat. Because we don't have time, not enough time, we are going to skip on. The enrichment is done normally by the method of gas centrifugation. It concentrates the uranium-235 or enriches uranium-235. The nuclear energy is produced by fission, as we said, and also that natural uranium only has 0.7%, and the rest is uranium-238. But the reactor uses a concentration of or enrichment from 3 to 5% uranium-235. The enrichment processes used are gaseous diffusion, which is less used now because it's costly. Now, the most enrichment doing in the world is by centrifuge in a gaseous form. And The third generation is going to be the laser excitation, but still we used gas centrifugation. We can see that the enrichment represents about 5% of all total cost of electricity generated at current prices. So it's costly, the enrichment process. The fuel fabrication is start with the UF6 enriched and transformed into a black oxide powder of uranium. It is compressed, sintered, and rectified to make pellets. These pellets are put together in tubing of normally an alloy made of zirconium named zircaloy, which is a very good in terms of heat conduction. Is not transparent to tritium movement. It has very good properties in terms of temperature of fusion. So it is mostly used as for containing the uranium pellets. So they are then grouped in bundles like those represented on in the right of the slide. Well, let's see. Then the fuel is irradiated in a nuclear reactor. We can see that we start with uranium-235 and uranium-238. The first has about 4%, and the other is 96%. At the end of the irradiation, we are also having 100%, but the percentages changed. First, the fission products are now 5%. Plutonium is 1%. Uranium-235 was reduced from 4 to 1%, and uranium-238 was also reduced from 96% to 23%. It is also produced plutonium, but as it is also consumed by activation or by fission, it at the end is reduced to 1%. To the right side of the slide, there is a figure representing the nuclear reactor with the nuclear core in yellow and red, and the other components of the nuclear power plant. Well, after the fuel is used in the nuclear reactor, it has to be stored temporarily in a spent pool, which contains, during several years, the spent fuel. Normally, these pools are inside water. I mean, the spent fuel is put all together to be cooled off. And the water serves as cooling fluid and as shielding. Normally, the storage is made for several years, but in 40 years of storage, the fuel radioactivity will be 1,000 times lower than when it was removed from the reactor. Well, let's talk about nuclear fuel reprocessing. The spent fuel contains, as we said, 96% uranium, 1% plutonium, and the rest is fission products. Some countries reprocess chemically this usable uranium and plutonium to separate them from the waste, from the fuel. The uranium, which is less than 1%, and the plutonium can be reduced. It can be converted as MOX fuel in fuel for nuclear reactors. I mean, it's a mixture of plutonium and uranium. The recovered plutonium mixed with uranium can be used as MOX fuel. And the right is a representation of the processes for reprocessing the uranium, the nuclear spent fuel. Well, the disposal of spent fuel or high-level wastes are to be pursued by several countries. This high-level waste can be safely disposed in deep underground stable rock formation. These formations can be granite and also other rocks. And this allows us to eliminate the risk to people and the environment, isolating this high-level waste for hundreds of thousands of years. Why these such long times? Well, because the main isotope for the isolation is plutonium-239, which has a half-life of 24,000 years. So we need to keep isolated for perhaps about 500,000 years. Normally, these deep geological formations and repositories have to be placed in a deep of more than 600 meters. The countries that are close to have the first repository for high-level waste are France, Finland, and Hungary. The waste is immobilized in glass inside metal canisters. The canister most feasible to be built with is bronze. Well, this is on the left, you have a representation of the fuel cycle, and the right is a representation of the use of the uranium or plutonium in weapons. This is a different side, but as this workshop is devoted to non-proliferation, we should be aware of.